All right, let's jump right in and investigate one of the deepest, most fundamental mysteries in all of physics, the arrow of time. I mean, why does it only seem to fly in one direction? Why can we remember the past but not the future? And really, why can't we just unbreak an egg?
You see this kind of thing happen every single day. A glass falls off the counter, it shatters into a million pieces. It's a perfect example of order turning into chaos. But have you ever, not once, seen the reverse happen? Have you ever witnessed those shards just leap off the floor, perfectly reassemble themselves, and land back on the table? Of course not. That would be absurd. But here's the thing. The basic laws of physics don't actually forbid it. So the real question we have to ask is, why not? So on one side, you've got events that look completely normal to us. An ice cube melts, an egg falls and breaks. Totally normal. But then you look at the reversed version, and it just looks wrong. Impossible, even. A puddle deciding to freeze itself while sucking smoke back into a log? No way. This really clear one-way street is what we call the thermodynamic arrow of time.
Okay, so our investigation begins. To get to the bottom of this, we have to start with our prime suspect. The rulebook for the entire universe. The fundamental laws of physics themselves. Surely the direction of time has to be written in there somewhere, right? And this is where our investigation immediately hits a really surprising snag. It's a principle called time reversal symmetry, or T-symmetry. And what it means is that, for the most part, the fundamental laws of physics, they just don't care about the direction of time. They work exactly the same forwards as they do backwards. You know, think about it this way. If I showed you a video of a planet orbiting a star, could you really tell me if I was playing it forwards or in reverse? Probably not. Either way would look completely realistic. And that's because the laws of gravity are T-symmetric. So if the laws themselves don't have a built-in arrow, our mystery just got a whole lot deeper.
So if the fundamental laws are time-symmetric, where in the world does its one-way street come from? Well, let's move on to our second suspect. And this one looks like a smoking gun. It's called entropy.
This is the famous Second Law of Thermodynamics. And what's so special about it is that it's one of the only principles in physics that does have a built-in direction. It says that in a closed system, like, say, the entire universe, the total amount of disorder, or entropy, is always increasing. Your clean room gets messy, not the other way around. Finally, we have a law that points the arrow of time firmly into the future. But this just creates a huge conflict, a puzzle known as Loschmidt's paradox. How can a universe that's governed by these tiny, time-reversible microscopic laws produce this giant, irreversible macroscopic world where entropy always goes up? How do you get a one-way street out of a set of rules that are all two-way? The answer to this paradox is pretty stunning, mostly because it reveals that we've been looking in the wrong place this whole time. The answer isn't in the rules of the game, it's in how the game was set up. The secret is all about the state of the universe at the very, very beginning. And this is the breakthrough. The breakthrough idea is called the past hypothesis, a name that was popularized by the philosopher of physics, David Albert. And let me tell you, it completely shifts our perspective on this entire problem. So what the past hypothesis says is actually pretty simple, but it's incredibly profound. It postulates that the universe, for some reason we don't understand, began in a state of unbelievably low entropy, a state of extreme, almost perfect order. Now, this isn't something we can derive from other laws. It's a brute fact, an assumption we have to make about the universe's starting conditions.
Let me give you an analogy to make this super clear. Imagine you have a box of gas, and all the molecules are somehow packed neatly into one tiny corner. That's a very highly ordered, low entropy state. Now, you come back a second later, and of course, they've spread out randomly to fill the whole box. That's a disordered, high entropy state. You would never, ever expect to see the reverse happen spontaneously, right? There are just way, way more ways for the gas to be disordered than ordered. So the only logical conclusion you can come to is that the ordered state had to have come first. And that, right there, is the core of the solution. The arrow of time isn't some fundamental property of the laws of physics. It's a consequence of our universe's origin story. It only exists because the universe was born in this incredibly special, highly ordered state. It's like the universe started with its cosmic room perfectly tidy, and it's just been getting messier ever since. But the implications of this go so much further than just why coffee gets cold or eggs break. The past hypothesis also helps us explain the other, more personal arrows of time that actually shape our lives, like our memories and our sense of cause and effect. See, if you look at how different physical variables behave when you mathematically reverse time, you find a pattern. Most of them are symmetric. They flip in a predictable way that still looks plausible. But then you get to entropy. It's the big outlier. It is fundamentally asymmetric. It only ever goes one way. And that's all because it's anchored to that super special low entropy starting point of our universe.
And this has massive consequences for how we experience reality. I mean, why can you remember what you had for breakfast yesterday, but you can't remember what you're going to have for dinner tomorrow? It's because the low-entropy past leaves behind these clear, ordered traces, things like records and memories. The high-entropy future is just too disordered for that. And it's the same reason we feel like we can influence the future, but the past is set in stone. It's all a downstream effect of the universe's one-of-a-kind starting point. So, we've solved it, right? Case closed. The past hypothesis explains the arrow of time. Well, yes and no. In solving one mystery, our investigation has accidentally uncovered an even deeper, more profound one. The physicist Roger Penrose calls this the greatest puzzle about the Big Bang. See, the real mystery isn't that entropy increases. Of course it does. That's just statistics. The real mystery is why it started so unbelievably low in the first place. Why was the universe born in such a fantastically improbable, highly ordered state? So what this means is that the past hypothesis is a description. It's not an explanation. It tells us what the universe's starting condition must have been for time to have an arrow, but it gives us absolutely no clue as to why it started that way. It's a fact we've had to add into our theories to make them match reality, but we can't actually explain it with any deeper principle. Not yet. And this leaves us right here, on the cutting edge of modern physics. Solving Penrose's puzzle might require a completely new theory of everything, maybe something like a complete theory of quantum gravity. What new physics will we need to finally explain why our universe was born with this one special condition, the very one that allows eggs to break but never unbreak, and the one that ultimately sets the arrow of time in flight? The investigation, as they say, continues.